Welcome to lecture 4 on number sets. The first number set we will consider is the set of natural numbers n. 0, 1, 2. These are the naturals. And we're not giving any definition of naturals, but we will just rely on the intuition of the numbers that we use for counting objects. The second number set is the set of relative integers, which are basically the natural numbers with a sign, plus or minus 1, plus or minus 2, so on and so forth. So these are the relative integers. The reason for introducing relative integers is that with the natural numbers we cannot carry out the subtraction of any two numbers. For example, if we do 1 minus 2, well, there is no natural numbers that will be the result of this subtraction. Instead, we can always perform the subtraction within z. By the way, z stands for Zahlen, which is the German word for numbers. The next number set that we will consider is the set of rationals, Q, which is basically the set of all fractions. So Q stands for quotient. And this set of fraction can be further specified as n divided by m, such that n belongs to z and m belongs to z minus 0. So this is the set of the rationals. The next set that we will introduce is the set of reals, and then we have complex numbers. Now, the reason for introducing Q after Z is that we cannot perform the division of any two relative integers within Z. So this is why we have introduced the Q, because now we can perform the division of any two numbers n and m, provided that m is not 0. The reason for introducing instead the real numbers after Q is that there are some operations that we cannot perform within Q. For example, the extraction of a square root. And then again, we introduce the complex numbers because within the real numbers we cannot perform the square root of a negative number, which instead can be done in the complex numbers. Now, you may wonder at this point, why stopping? Why don't we introduce other number sets? The reason is that we can do pretty much everything in the complex numbers. So this is a good point where to stop. Now, for us, it will be particularly important, this set of real numbers, and we want now to focus more on real numbers. So let's give now a proper definition of real numbers. And we will say that the real numbers are a quatern R with two operations, sum and product, and an ordering criteria. Characterize by three types of axioms: algebraic axioms, ordering axioms, and continuity axioms. So what we are doing now is, instead of attempting a definition of real numbers, we are saying that the real numbers are characterized by some axioms. So this is an indirect way of defining real numbers. And we will now analyze in detail each set of axioms. So let's start with the algebraic axioms. So the algebraic axioms define basically the triple R with the two operation. So in other words, we are now just focusing on the first three elements of the quadrant. Okay, R is the set of numbers, and sum and product are the two operations defined on this set of numbers. And basically this triple R plus and times are a field which is to say that the binary operations sum and product they satisfy the following properties. Okay, so we have 9 properties now. So let's start with S1, where S stands for sum. So S stands for sum. S1 is the first axiom that refers to the sum of any two numbers, and this axiom says that a plus b is equal to b plus a for any a in R and for every b in R. And this is what is usually called the commutative property of the sum. So this is a first property that is satisfied by the operation plus, by the sum operation. The second axiom that refers to the sum is that a plus b plus c is equal to a plus b plus c. And again, of course, this is true for every a. I'm not saying that for every a in R and every b in R. And this is what we call the associative property of the sum. As a result of this, by the way, as a result of this, we can also say that we can just write a plus b plus c, as it doesn't make any difference if we do the sum of a plus b first and then sum c, or if we do b plus c first and then we'll sum with a. Okay, so next axiom is S3, is there exists a real number 0, which we'll call in this way 0, such that a plus 0 is equal to a for every a that belongs to R. And this is this number 0 is what is called the neutral element. So we are postulating the existence of a neutral element 0 such that whatever real number we pick, if we sum the real number with 0, we get the real number. The fourth axiom for the sum operation says that for every a real number, there exists a b real number such that a plus b is equal to 0, and this is basically the existence of the opposite element. So we are saying that for every real number a we can pick randomly, there will be another real number b which will be the opposite of a. We are not saying that there exists only a unique opposite. We are saying that there at least there exists one opposite, and this will complete the list of the axioms that refer to the sum. Let's now move to the axioms for the product. We have a first axiom, P1, which says that A times B is equal to B times A. And we recognize, of course, once again, the commutative property for the product. Then we have P2 that says that A times B times C is equal to A times B times C, and this will be the associative property of the product. Then we go to P3. The third axiom for the product is the existence of an element 1 that belongs to the real numbers such that A times 1 is equal to A. And of course this has to be true for every A belonging to the real number, and this is the neutral element for the product. And finally we have P4, which says that for every A that belongs now to R minus 0, there exists a B, another real number B, such that A times B is equal to 1. And this is the existence of the inverse element. And again, we are not saying that there exists a unique inverse, but we say that there exists at least one inverse element. We will prove later that both the opposite and the inverse elements are unique for every real number. We have an additional axiom, which is so-called the distributive property, D, which says that A times B plus C is equal to A times B plus A times C. And as you see, this distributive property binds together the sum and the product in one single property. Okay, so let's review quickly some of these axioms and some of these properties basically. So for example, we realize immediately that the S4 is something which is definitely not in the natural number. in the sense that the existence of the opposite cannot be guaranteed within the natural numbers, but it is something that we can also find in Z and Q. If instead we look at P4, P4, well, P4 is something that is not in Z, right? In fact, if we stay in Z, which is the set of relative integers, we cannot find the inverse of any number in Z. So up to this point, it seems that these properties that we are defined for the field of real numbers, together with the operations of sum and product, they have nothing peculiar to real numbers, but they might also be true for relative integers. But let's keep moving, and let's now pass to the other set of axioms, which are called the ordering axioms. Okay, so the ordering axioms are related with the relation, the ordering relation larger than or equal. Okay, this is the sign, which has the following properties. Okay, so we'll call these properties, because they are related to the ordering, ord1, ord2, ord3, and ord4. So we will have 4 properties for the ordering. Okay, so the first one says that for every x in R and for every y in R, there must be x larger than or equal to y, or y larger than or equal to x. And this is what is usually referred as total ordering, meaning that whatever couple of numbers x and y we pick, we can always compare them with respect to the ordering criteria. The second axioms of the ordering says that for every x in R, and it must be that x is larger than or equal to x. So this is usually referred as the reflective property, saying that you can compare any real number with itself. Third property says that if x is larger than or equal to y, and y is larger than or equal to x, then it follows that x must be equal to y. And this goes under the name of anti-symmetric property. So we are saying that if x is larger than or equal to y and y is larger than or equal to x, it must be that x is equal to y. The fourth ordering property says that if x is larger than or equal to y and y is larger than or equal to z, then x is larger than or equal to z. And this is what is referred to as transitive property of the ordering. Good. Now, um, now, now that we have listed all the axioms, there are also other two properties that uh, basically put together the ordering with the operations of sum and product. Because remember that we have defined basically the quotern R plus times and the relationship. So we can introduce now two additional properties, and I will call basically, so we can say that the ordering is related to the operations plus and times by two properties. And I'm going to call the first one OS, meaning that this O stands for ordering and this stands for sum. So OS is just a property that relates the ordering with the sum. And this property is the following. If fx is larger than or equal to y, then x plus z is larger than or equal to y plus z. And this has to hold for every z belonging to the real number. So we're just saying that if x is larger than or equal to y, we can add on both sides a third number z, and we still have the same inequality, the same ordering. The second axiom is, now of course this is something that we have expressed in a quite straightforward manner, but if we had to be more formal, we should say that this should be expressed as follows: for every x into the real number, for every y real number, for every z into the real number, the fact that x is larger than or equal to y implies that x plus z is larger than or equal of y plus z. Okay, so this is just a more formal way of representing exactly the same property. The second axiom, we will call this OP, because now it will be referring to the ordering and to the product. So this second property says that if x is larger than or equal to y and z is larger than or equal to 0, then we have that x times z is larger than or equal to y z, and this has to hold for every z that belongs to the real number. Let me say that this is R0 for every z that belongs basically to the positive real numbers. Good. So again, we can try to express this more formally by saying that for every x that belongs to the real number, for every y that belongs to the real number, and for every z that belongs to our, let me say that this is, let me call this plus 0, to say that this is the set of a positive real numbers with the 0 included. We can say that x larger than or equal to y. This has to be verified together with the fact that the z must be larger than or equal to 0. So this implies that x times z is larger than or equal of yz. Good. So now at first sight it might seem that all these axioms are quite useless for the practice of calculating inequalities or equalities or using just the real numbers, but actually we keep using them all the time without realizing. Let me give you an example of this. Let's suppose that we need to solve the following simple inequality: 3x plus 5 larger than or equal to 7. Okay? Well, how do we solve this inequality? Well, we'll bring 5 to the right hand side, and then we will easily divide by 3, and we get x larger than or equal to divide by 3. Okay, so this was the easy way, this is the practical way of solving the inequality. And I'll show you now that hidden in this step, we are using all the properties that we have just introduced. In fact, starting from 3x plus 5 larger than or equal to 7, the first thing that we do is applying the OS axioms, that basically is saying that given x and given y, we can, and x larger than or equal to y, we can add on both sides and third real number z. Well, in this case we can add on both sides minus 5. We have used now the OS property. And now by using the fact that 5 minus 5 can be calculated first, which is nothing else that S2, the associative property of the sum, we can write that 3x plus 5 minus 5 is larger than or equal to 2. This is what we are left on the right hand side. And now using the definition of the opposite, which is S4, the S4 defines the existence of the opposite of any real number. Minus 5 is the opposite of 5. We know that this is just 3x larger than or equal to 2. At this point we should multiply both sides by 1/3. So we have 1/3 times 3x larger than or equal 1/3 times 2. And let's say that at this point we should prove, okay, let's say that we should prove that 1/3 is larger than or equal to 0, right? So so we are using now the OP, which is the axioms that says that if we multiply both sides by a positive number z larger than or equal to 0, then we still have the same inequality. And now, recognizing that 1/3 times 3 times x is larger than or equal to 2/3, and we are now using the associative property of the product, which is P2, and realizing that again 1/3 is just the inverse of 3, we finally get x larger than or equal to 2 divided by 3. So we are still using now P4. So you see that we have solved the inequality, and hidden in every step is the application of all the axioms that we have just introduced. Now, as a side note, I want to highlight the fact that there are many properties of real numbers that are commonly used, which are not given in the axioms. So for example, the fact that the opposite minus a of a real number a and the inverse 1 over a of a real number a different from 0 are unique. We didn't say this in the axioms. We only said that there is at least one opposite, there is at least one inverse for a real number different from 0. So we should prove now that these two elements, opposite and inverse, are unique for every real number. Another property that we didn't mention in the axioms is the fact that the 0, which is the neutral element for the sum, and 1, which is the neutral element for the product, are unique. And also the fact that the 0 is different from 1, or that 1 is larger than or equal to 0. And finally, another very useful property is that if x is larger than or equal to y and z is less than or equal to 0, then the sign of the inequality changes when we do the product. xz is less than or equal of yz. All these properties can be derived from the axioms, and we'll do some of this later. But this is just to say that the number of axioms are kept as less as possible. Okay, we could have included all these properties in the axioms, but it is much better to have as less as possible axioms and deriving all the properties later. Good. There is one final axiom, very important, which makes the difference between the real numbers and all the other sets, and in particular makes a difference between the real numbers and the rational numbers. And this is what is called the continuity algorithm. Axiom. Now, in order to introduce the continuity axiom, let me first give a definition. So let A be a subset of the real numbers. Let B another subset of the real numbers. So these are B two subsets of R. We say that A is at the left of B. Okay, we say that A is at the left of B if the following happens: for every A that belongs to A and for every B that belongs to B, it is A less than or equal to B. So this is the fundamental property that characterizes the fact that A is at the left of B. So let's make a drawing here. Let's suppose that we have A defined with the blue, and we have B, for example, defined here. So if we pick any element in A, any element in A should be to the left of any element in B. So This is the idea, right? So that brutally we can say that every element in A is less than or equal any element in B, okay, which is expressed formally by this statement. Okay, so now that we have the definition of what A to the left of B means, let's give the continuity axiom, the continuity axiom. If A is at the left of B, then there exists at least one point C, of course a real number C, such that for every A that belongs to A is less than or equal to C, and for every B that belongs to B, C is less than or equal to B. So this is basically the continuity axiom. These are the properties of this point C, which is just like saying, okay, we have the real line, we have A here, and we know that A is to the right of another set B, whatever it is. We are saying that there exists at least one point C that basically separates the two sets, because it will be less than or equal of any point that belongs to B, and will be any point in A will be less than or equal to C. So this point is the separation point. And note this is an important thing to realize. In Q, in the set of the rational numbers, the continuity axiom does not hold. And there is an easy way to see this. I'm not giving a formal proof of this, but let's consider, for example, the two sets A of all the rational numbers such that x is larger than or equal to 0 and x to the square is less than or equal to 2. So this is basically the set of rationals which are positive, but such that their square is less than or equal to 2. And then we'll consider B as all the rational numbers such that x is still larger than or equal to 0, but the square now is larger than or equal to 2. Okay, so it can be shown that two things. First, A is at the left of B. Now, why is that? Well, clearly A is the elements of A are elements such that the square is less than or equal to 2, right? B is the element is made of the elements of the rationals whose square is larger than or equal to 2. So clearly every element in A is to the left of every element in B, right? Because if a rational number has its own square, which is less than or equal to 2, and the other ones are larger than or equal to 2, clearly one is to the left of the other. So the second is that there is no rational numbers C in between. In fact, in that case, this separation point C should be such that C to the square is equal to 2, but this is impossible in Q, right? So there is no separation point, so the continuity axioms does not hold. So far we have characterized real numbers with some axioms, but we actually never proved the existence of real numbers. Likely there is a theorem that proves exactly this. It proves the existence of real numbers. We are not providing a proof for this theorem, which is very difficult, but we are just stating the theorem. So basically the theorem says that there exists a quaternion R plus times which satisfies all the axioms. So with this theorem we know that there exists a number set R that is able to, along with the binary operation of sum and product and the ordering criterion, that satisfies all the axioms. And there is another theorem that says that basically there is only one such set. So this is the theorem on uniqueness of the real numbers. We are not going to prove this theorem, but we'll just give an idea of what is behind the proof of this theorem. It will be basically proving that, assuming that if we assume that there exist two quaterns, let's say R plus times, so this is the first quatern, and let's say that we have another quatern, R circle plus circle times circle and larger than or equal circle. So we are assuming that there exist two quaterns that satisfy all the axioms. We can find a bijective function f that goes from the first set to the second set, a bijection, so a 1-1 mapping between the two sets, which commutes with respect to the ordering operations, which in other terms means that if we have f of x plus y, this would be just equal to f of x plus f of y. So what I'm writing is that I will start with two elements in the first set R, and I will evaluate the sum, which is another element in R. Then I take the image through F, and of course I will get now an element that belongs to our circle. Now it turns out that this element that belongs to our circle can be obtained by applying the circle sum between two elements in the R circle, and these two elements are just the image of F of the original X and Y elements. So this is to say that we can map every possible sum in the R set to another sum that happens into the other set. Another property of this function should be that f of x times y, we are now performing the product of two elements of R, and we are mapping this product to f of x times circle with f of y. So this is another example, because we are once again taking two elements of R, x and y, and making the product of this, and then sending through f into an element of our circle. And it turns out that this image, this element of our circle, can be also obtained by just taking the circle product between two elements of our circle, which turn out to be exactly the image through f of the original elements x and y. Last property would be that if x is larger than or equal to y, this is possible if and only if f of x is larger than or equal, according to the second criteria of ordering, f of y. So if such a function exists, if such a bijection exists between the two sets R and R circle with these properties, we say that we have an isomorphism. This is an isomorphism in the sense that the first quaternion is isomorphic with the second quaternion. So we have a one-to-one map, and so basically the two quaternions are totally equivalent because each element of the first can be mapped to each element of the second. Right, so with this we conclude our review of all the properties of real numbers, and in the next lecture we'll keep on introducing other properties of number sets, very important properties like upper bounds and lower bounds. So see you next time.